Hello everyone, I hope you're doing well. So in today's video, we'll be going through the 2019 Northern Hemisphere Physics exam short answer questions part 2, where we pretty much go through questions 11 and questions 19 if I'm not mistaken. So like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. I hope this video finds you well and helps you as much as it's going to help most of my students. So yeah. Let's smash through this video. Question 11. Kim and Roger conduct an experiment to observe an electron diffraction pattern. 500 electrovolts electrons are projected through a diffracting grid and the resulting pattern is observed on the screen. Basically, when you do this experiment, you'll get something that will look like this basically. A diffraction pattern that looks like this. So like that. Something like this. That's what it should look like. All right. And that's what it looks. So that's what basically when you when electrons are pretty much hit on a crystal, it pretty much produces a diffraction pattern that looks like this. Okay. So, and the resulting pattern is observed on the screen. Kim and Roger want to calculate the wavelength of X-rays that would produce a similarly spaced diffraction pattern. Okay. So, if this is the diffraction pattern of the electrons basically, and they want to pretty much have basically the similar spacing as, so they pretty much want to have similar spacing for X-ray that has the same as our electrons. What do they need to have? They must have the same wavelength basically. They must have the same wavelength and also the same momentum, because momentum is h over wavelength, where h is of course a constant. So if your wavelength is the same, if we need the wavelength to be the same, the momentum must also be the same. So basically, this is what we're trying to explain. If basically Kim and Roger want to produce a similarly spaced diffraction pattern that basically looks like the electron one for the X-ray, they need to have the wavelength to be the same as the electrons and the momentum. That's the key. All right. So Kim says that they will need an X-ray of 500 electrovolts. Rubbish. Energy is going to be different. So the energy of electrons is going to be totally different to the energy of the X-rays. That's wrong. Roger says that X-rays of a different energy will be needed. Yes, Roger's pretty much correct, because all you need is to be the same is basically the momentum and the wavelength. So let's write that down. So explain why Roger is correct. Basically, yeah, Roger is correct because they're going to have different energies basically. So all we need to have is for them to have the same diffraction pattern is that the wavelength must be the same and the momentum, but the energies are going to be different basically. So that's all we need to kind of summarize. For electrons, so basically electron diffraction actually, pattern to be similarly spaced to an X-ray, the wavelength and momentum must be the same. Be the same for both. The same for both. But the energies are going to be different. So basically, yeah, Roger has explained that. The energy is going to be different, but only the X-rays and the wavelength must be the same. So beautiful. B, showing each of the steps involved in your working out, calculate the energy of the X-rays that would be required to produce the similarly spaced diffraction pattern. Like we said, all right, so we have 500 electrovolts of electrons. So that's basically our kinetic energy. So let's transform it back to joules. So in terms of joules, so we know that 5,000 electrovolts, if I multiply it by 1.6 times 10 to the power of negative 19, it's going to basically transform it back to joules. So 5,000 times 1.6 times 10 to the negative 19. That gives me basically 8 times 10 to the power of negative 16 joules of energy. And so, looking at my formula sheet, as we said, the momentum is going to be the same for both. So what we can do is the momentum formula, especially the square root of 2m kinetic energy. Well, of course, this is your kinetic energy. I should write it as kinetic actual energy. So, okay. So we're going to write that down. So 2 times the mass of the electron, which is 9.1 times 10 to the negative 31, times the energy of the kinetic energy of the electrons. So that's going to give me what? Square root 2 times 9.1 times 10 to the negative 31 times that. That basically gives me, as momentum, 3.81 times 10 to the negative 23 kilograms meters per second, basically. Now, we've got that, and so if I look at my formula sheet, if I want the basically the energy of a photon, it's basically P, your momentum, times your speed of light. So what I can do is basically multiply those two. .0 times 10 to the power of 8. And that's going to give me, it's going to give me, in terms of joules, 1.144 times 10 to the power of negative 14 joules. Now, make sure we want to have it in electrovolt. So we basically want to do is we want to divide that by basically 1.6 times 10 to the negative 19. So let's do that. So I'm going to just pretty much put it here. Also want to divide this 1.6 times 10 to the negative 19 to get it into basically electrovolts. And so I get my answer. It's basically 7.2 times 10 to the power of 4 to the power of 4. Beautiful. Done. Question 12. Optical fibers are constructed using transparent materials with different refractive indices. A laser light beam of wavelength 590 nanometers is shown into the fiber and travels along the narrowed pathway shown in figure 11. For the fiber to operate as designed, which must have a greater refractive index, the cladding or the core? So basically, the design of an optical fiber is it goes through the process of internal reflection, basically. Total internal reflection. So it doesn't actually pass through the cladding, but it goes through internal reflection. So it uses the process of basically critical angle. It uses the process of the critical angle, actually, in this case. So if I want to know which one will have a greater, which one, has to have a greater refractive index, the cladding or the core, what I'm going to do, actually, let's think about it. I am going to do this. So let's assume that the core is our greater refractive index. So I'm going to write it as 1.5 in this case. And our cladding is our lower one. So let's say 1.0. Let's try to use remember how we want our critical angle? It's so basically it uses the critical angle. So optical fibers use the concept of total internal reflection, which uses the critical angle pretty much. So what I'm going to basically try to do in this case is, all right, let's think about it. So it's going to be N1, which is basically the core, 1.5. Sine your critical angle, theta C, is equal to 1.0. That's assuming that the core is the has the greater refractive index. So that's going to give me 1.0 divided by 1.5, and the sine inverse of that, I get basically 42 degrees using that. So I get 42 degrees. So I actually get an angle. So that's good. What about if I do the opposite now? Have a look at this. If I basically switch them around now, I make the cladding to have the higher refractive index, and I have this one, the core, to be the lower. Have it try this now. So it's going to be basically 1 sine theta C must equal to 1.5. And this actually, try it. So sine inverse of 1.5. It's your pretty much your calculator should say error, because you don't need to know, because this is maths. If it says error, it basically means that it doesn't make sense. So basically the core has to be the higher refractive index, because the other way around doesn't work. Your calculator says it doesn't work. So choose basically the core. If you really want to understand why, basically because sine theta can only exist only exists between -1 to 1. What we've done is we have 1.5, which goes above this actual range of sign. So that's why it doesn't actually fit into it. So absolutely. So the core would be the main answer. That's how I would do it in an exam, basically. Just put, I mean, you only got a 50% chance, so it's quite easy to do that. All right. The refractive index of the cladding is 1.42. All right. The critical angle for the light striking the core cladding boundary is 66. Calculate the refractive index of the core material. Beautiful. So we want to calculate basically N1. Sine your critical angle, which is 66, is equal to N2, which is basically the cladding, which is 1.42. And that's going to give me 1.42 sine 66, 1.55. Easy. Beautiful. Question 13. A seawall that is aligned north and south protects a harbor of constant depth from a large ocean waves, as shown in figure 11. The seawall has two gaps, S1 and S2, which are 60 centimeters apart. Inside the labor, a small boat sails north parallel to the seawall at a distance of 420 meters from the seawall. At point C sits a beacon equidistant from the two gaps in the seawall. So basically, look, just from looking at this straight away, you should realize that this is like the double split experiment, basically, Young's double split experiment. The boat's captain noticed that about every 42 meters, there's a calm water. Well, there's large waves between them. Basically, this is your change in x. This is the distance between basically your nodes or your antinodes, basically. So that's actually your change in x, because it tells us that the captain noticed that about every 42 minutes, there's calm waters. And of course, in between them, there must be large waves, basically. So basically, this is your node. Okay, we've got that. So that's your change in x. That's good. All right. Will the beacon at point C be in the calm water or the large water? I'll give you an example. This is so easy. It's actually, so your point C is equidistant from both sources. What do we know? It means that the path difference must be 0. So constructive interference happens at point C. Basically, what it will mean is large waves will basically be at point C. That's it. Easy. This is one of the most common question you get in exams, so it's very easy to get full marks for this. So all you have to say basically, we'll say is large waves as path difference is 0, basically hence constructive interference occurs at C. Beautiful. Calculate the wavelength of the ocean waves to show working out. Easy. We're given the length between the slits and the actual thing. We're given the distance between the slits, basically, which is your D. And we're also given your change in x. So we can easily calculate our wavelength using, basically, your change in x is equal to lambda, which is your wavelength times your distance over your D. So basically, if I know my change in x is what? 42 is equal to your lambda. L is what? 420 all over your distance between the two slits is 60. That's going to give me 120. That gives me 6.0 meters, basically. That's my wavelength. Easy. Question 14. Figure 13 shows a simple apparatus that can be used to determine the frequency of a tuning fork. Alright. The apparatus consists of two supports and a metal wire that is stretched between a fixed peg and hanging weight. The wire is under tension, okay? The tuning fork is set vibrating and is then touched onto the wire close to the left-hand support, which makes the wire vibrate at the same frequency as the tuning fork. Alright. Draw the diagram of a simpler standing wave pattern that can exist on a vibrating section of the wire, which is the fundamental, yes, when n equals 1. That's the simplest standing wave between the two supports. So basically between these two supports, what do we see? They are close on both ends. And it's quite easy. So the fundamental waves between two close ends is what? So if I draw these, looks like this. This is the fundamental wave. will basically look like this. Oops, that's not. That's what the fundamental wave basically looks like, where it's basically n equals 1. That's, yeah, so draw the diagram of a simple standing wave that can exist on the vibrating section of the wire between the two supports. So these here are they are closed, basically. And yeah, having a look at my formula sheet. Yes. When you have two fixed ends, basically, as you see, two fixed ends, that's how it should look like. Easy. Okay, perfect. When the distance between the supports, so the distance, your L, basically the distance between these and that, is 0.92 meters. The fundamental frequency resonates in the wire. So the fundamental is when n equals 1, like we said. Calculate the wavelength of the fundamental. All right, so looking at my formula sheet, so summary sheet, it says, okay, with fixed ends, your wavelength can be calculated basically by 2L over n. So basically, what's our length, which is 0.92, and n is our fundamental, which is 1, basically. That's going to give me 1.84 meters. Calculate the frequency of the tuning fork if the speed of the waves in the wire is 224 meters per second. So the frequency. So for fixed end, the frequency formula is NV over 2L. Well, of course, n is 1, and the velocity is, they said, 224. 2 times your length, which is 0.92. 0.92. That gives me basically 122 hertz. Beautiful. Question 15. Figure 14 shows the energy level diagram for a hydrogen atom. All right, so we're given this. Beautiful. The hydrogen atom is excited from the ground state, so from here, to a higher energy level. Substantially, it makes a transition from this higher level to n equals 3 energy level, emitting a photon of wavelength this. What was the number n of the energy level before the photon was emitted? Show your working. All right, so basically, it started off the ground state and it basically went to a higher energy state. Now, there's so many possibilities. It could have went to this one. It could have went to this one. Could have went to that one. Just many energy states. But we are 100% certain that as it is one of these energy states, it emits, when it goes down to n equals 3, basically, and it emits 1,242 nanometers. Basically, energy. There's going to be energy. And that's what we're going to try to calculate. How much electrovolts of energy has it released? As it went from some value to, yeah, n equals 3. So, let's do that. Beautiful. So, I'm looking at my formula. Let's go formula sheet. Alright, so I'm given the wavelength, so I can easily calculate the electron. So, the energy of a photon is basically hc over wavelength, basically. So, if I want to calculate that energy, so I want to write h in terms of, so 4.14 times 10 to the negative 15, it says, times your c value, which is your speed of light, all being divided by your wavelength. So which is 1,242 nanometers, which is times 10 to the negative 9 to convert it to meters. That's going to give me 4.14 times 10 to the negative 15, 3.0 times 10 to the power 8, and 1,242 times 10 to the negative 9. Basically, it gives me 1 electrovolt. So basically, it's emitted 1 electrovolt. How can that happen? So which one has that? So basically, think about this. So it cannot be n equals 2. So basically, of course, it cannot be n equals 2 because it has to be one of these here. Because it goes down to n equals 3. So let's say if it was n equals 4. If it goes down to n equals 3, how much energy does it emit? It emits 0.7 electrovolts, not 1 electrovolts. That's wrong. What about 5? So 13.1 minus 12.1. Yes, that is 1 electrovolt. So your actual value of n was n equals 5, basically. So it's, yeah, that's your energy level. N equals 5. Beautiful. Done. Next question. The quantized states of an electron of a hydrogen atom provides evidence of the wave particle duality of electron. True. Describe how an electron in an allowed state is modeled. To provide this evidence, you might include a diagram. Beautiful. Basically, they're just trying to tell you, prove or explain the electron standing waves, how electron standing waves are formed. So one of the most kind of common questions, so make sure you write this in your formula sheet, because it's whenever you see a question like this, make sure you dot point those specific answers so you can get the marks. So let me explain what it is. So we know that pretty much the wave model states that electrons have a de Broglie wavelength. That's what the wave model states. And for a stable orbit to exist, a standing wave must form, where for a standing wave to form, the circumference, so basically the circumference of the orbit must be an integer multiple of the wavelength. This pretty much means, what does this pretty much mean actually? This pretty much means that only certain or discrete wavelengths are able to create a standing wave. So not all basically values or wavelengths are able to create a standing wave. Only certain or discrete, certain means basically discrete, only certain values are able to create a standing wave. And basically, if we know that we have discrete wavelengths, or certain wavelengths that are allowed, it also tells us, because we know that wavelength relates basically to hc over lambda. If this is discrete, it also tells us that your energy must also be discrete. So overall, this proves that only certain and discrete energy levels are allowed to exist. Because if only certain allowed wavelengths are allowed to exist, this also tells us that only certain basically energy levels are allowed to exist too. And so that's what it pretty much explains. And it's very nice and easy to get full marks in this question, because it's very important to write a nice kind of explanation of all this in your formula sheet. So I'm going to write a nice answer to this part here. And yeah, pick all those important parts. I'm going to be very detailing in this question 3. So yeah. And so this is, I'm looking at my summary sheet, basically. I hope that makes sense. So let's do, okay. So, and we'll also include a diagram, basically. See, the wave model of electron states that an electron has a de Broglie wavelength. So, for stable orbits to exist, a standing wave must form, basically, where the circumference of the orbit is an integer multiple of the wavelength. And so basically this whole formula describes what it is. So it's n wavelength equals 2 pi r, the circumference. So also, since only certain discrete, or you can say discrete, electron wavelengths are able to exist, and wavelength, so my hand actually hurts, so able to exist, and wavelength also relates to energy. Only, so we can say only discrete energy levels of electrons are allowed to exist. Beautiful. I mean, that goes in very depth of what it is. And yeah, if you want to include a diagram, it's very easy. So basically, let's just nicely include a diagram. Basically, you want to draw something like this, and let's say, okay, so like a nice, basically like this. Something like that. And let's draw basically the other part. So it must be crossing these here. Basically, that's what it looks like. I mean, these are, you want to dot that, but yeah, that's how basically it looks like. This one is basically, it has basically 4 wavelengths. So n equals 4, where n equals 4, because there's 1, 2, 3, and 4. Beautiful. That's just a basic diagram that you can draw. And yeah, perfect. Easy. Question 16, let's have a look at this. April sets up the apparatus shown in figure 15 to investigate the photoelectrical effect. She can change the frequency of light incident on the metal plate by changing the filter, and she could change the type of metal of which she can play. Okay, that's nice. Next thing she says is, for her first experiment, April chooses a filter that gives a frequency of this and a metal plate made up of cesium with a work function of this. April adjusts the voltage of the collector electrode so that the current becomes smaller and smaller when the ammeter reaches 0. April records the voltage shown in the voltmeter. Use your calculation to determine that voltage. But actually, she's trying to determine what the stopping voltage is. So I'm going to look at the formula for stopping voltage. Now, we know that the stopping basically voltage, where is the stopping voltage? So, okay, we know that the stopping voltage, which is your EK max, is equal to your HF minus your work function. So we're given the work function, and we're also given the frequency. Of course, H is what? 4 point. That's also your stopping voltage. Your EK max is basically your stopping voltage in a way. So 4.14 times 10 to the negative 15 times your frequency. How much we're giving it? We're giving it 7.13 times 10 to the power of 14 minus your work function, which is 1.95. That's going to give me what? 4.14 times 10 to the negative 15. 7.13 times 10 to the power of 14 minus 1.95. That gives it basically 1 volt. So 1 volt. Basically 1 volt of energy. Easy. Next question. For her second experiment, April uses a metal plate of zinc. Zinc has a threshold frequency for emission of photoelectrons of this. Photoelectrons are emitted, okay? Calculate the maximum wavelength in nanometers of the light for photoelectrons to be emitted from the zinc plate. Easy. We're basically given the wave frequency, so we can easily calculate the wavelength from velocity is equal to your frequency times your wavelength. And we know the velocity of these photons are the speed of light. So basically, it's going to be your wavelength is your velocity over your frequency. So your velocity is 3.0 times 10 to the power of 8, all being divided by your frequency, which is 1.04 times 10 to the power of 15. And that gives me basically, I want it in nanometers, sometimes 10 to the power of 9. That gives me 288 basically. Easy. So for her third experiment, April changes the metal plate from the zinc plate used in the second experiment to a plate of platinum. Platinum has a threshold frequency of 1.3 times 10 to the power 15 hertz. April uses light of frequency of this. So basically, just from looking at it, she's using a frequency that's below the threshold frequency, so there should be no photoelectrons emitted, but does not make any other changes. Photoelectrons are not emitted. Basically, yeah, as we predicted. Of course, if you're providing frequency that is lower than your threshold frequency, there's not going to be photoelectrons emitted. April observes for a longer time and then increases the intensity of light beam, but still finds that the photoelectrons are not emitted. So what she believes is she's pretty much believing the wave model of light. So she's believing that basically having, like what it pretty much states. So the wave model, let me explain the wave model, what it says. So the wave model of light basically suggests that you have electrons and basically we have waves, and these waves carry energy. And this energy is basically by its frequency. So having a high frequency means you're having a high energy, basically. So what she predicts is that any frequency, so having low frequency in this case, low frequency means low energy. She believes that having a low frequency and leaving it for long periods of time to this electron would kind of gradually let the electron kind of absorb it until it overcomes that work function for it to be released, which is wrong. That's not how it works, because there's existence of a threshold frequency. That's not how it works. So that's what she's basically thinking. She's thinking that that's why she's basically put it for a long time. So she thinks that it can, so she wants electrons to absorb as much of the energy, and she also increases the intensity. It's pretty much, yeah. So she believes that, and of course it won't work because there's an existence of a threshold frequency. Explain how April's observation support the particle model of light, but does not support the wave model of light in explaining the photoelectrical. That's what we just pretty much explained. As we said, basically, whatever we just explained right now kind of explained the question. So we basically explained how the wave model does not support it, because she's believing that, yeah, you know, low frequency or any frequency, putting it for long periods of time should gradually make electrons emit, which is wrong. So now we're going to explain why the particle model basically predicts. So the particle model is great because it supports the theory of the threshold frequency. So what is the difference between the photons and it? Like, what's the difference between the particle model? So basically, it states that if you have basically photons carry specific energy. So let's say it carries, I don't know, 2 electrovolts. We're making up values here. So this is a photon, and say we have an electron here. And this is our electron that we want to emit, basically. We want it to release. So, let's say the work function for this here is 3 electrovolts. Basically, what it says, the photon theory states, or the particle model, is that basically a photon carries a specific energy that's discrete, or basically proportional to its frequency. Basically, what do we mean by this? So basically, it carries a specific frequency, basically. And so, or energy, frequency is related to energy. So it carries a specific energy, and if it kind of collides, remember protons, one photon can collide with 1 electron. They can only do it one by one. So what it pretty much predicts is that this one photon, when it collides with its electron, it will give all of its energy to the electron. But what do we know? Its energy is less than the work function. Pretty much it won't be released. So, but what about the other case? What about if we make sure maybe we have 4 electrovolts? So now we have basically this photon carries a energy that's greater than the work function. Then it basically will let the electron basically go, basically emit. And that's what the difference between those two. So yeah, I'm gonna very much summarize this in a very deep detail just to help you out. I'm gonna use my summary sheet to actually summarize this. And yeah, make sure when you're in exam, I'm gonna give you a very deep analysis of what I just said right now to make it easier. And I hope you read this and understand, to fully grasp the knowledge of what this talks about. So, all right. So we're gonna say what to say. So we're gonna say April's observations. April's observation disapproves, as we said. So it disapproves the wave model. Because a wave can deliver energy continuously, basically, energy continuously to an electron, absorbing it, basically. So absorbing it. This means that even though a lower frequency wave carries less energy, all frequencies of light should produce a photocurrent given sufficient time. That's what basically the model, wave model predicts. But she's done that. She's given it as many times as, she's given it a longer time and still nothing has happened. But, we're going to say, but a threshold frequency exists. Light of a frequency, basically, of a frequency less than the threshold. So light less than the threshold frequency will not emit photoelectrons no matter how long the light. Okay, so the light is incident on the metal, basically. On the metal, and which she has done, basically. Which she has done. So here is kind of, we've gone into like this deep analysis of why it doesn't work. Because, yeah, the wave model basically it doesn't support it. Now we're going to basically talk about how the particle model supports it. Let's write it in a different color. So I'm going to put this down, actually. It's because it's a law, so I'm going to kind of bring this. Oops, I'm going to... Alright, bring this here. Alright, there. I'm going to write the next part. So basically the next part, which is how the particle model supports it. So we're going to say the threshold frequency supports the particle model as so a photon energy is discrete and proportional to its frequency. Just so it provides that a single electron will absorb a single photon. So it will absorb a single photon, and if that photon energy is less than the work function of the metal, the electron will not be emitted. And no photocurrent will be produced. Beautiful. That is it. I mean, that goes into very deep kind of analysis of all of it. And I hope if you read it and understand it, that will, yeah, if you're struggling with this concept still, I think this kind of summarizes why basically the wave model kind of fails to predict some stuff about the photoelectrical effect. So easy. Make sure you have that in your summary sheet, and that's it. Nice and easy. Question 11. Let's have a look at this question. All right. A spaceship is traveling from Earth to a star Epsilon, which is located 10.5 light years from Earth as measured by the Earth Space Instrument. So let's think about this. So we basically have Earth here. Let's draw. This is Earth, and say this is the spaceship. And let's say this is Epsilon. And so the distance between them, that's measured by what? Which is 10.5 light years. And that's kind of crooked. .5. So oopsies, let me write that here. 10.5 light years, and basically that's what's happening. Alright. Okay. So if the spaceship travels at this velocity, so basically to epsilon, basically, so that 0.85 c, determine the duration of flight as measured by the astronauts on the space traveling to epsilon. Take one light to be this. So basically what we're trying to find is the time that's measured by the astronauts. Okay, now what do we know? We know that the length that's measured by the astronauts is going to be the contracted length, because they're going to see that this length is shorter for them. So it means that this here must be your proper length. We also know that if this is your proper length, this must be also your dilated time, and this here must be your proper time. So basically, these astronauts are going to be measuring your proper time. So that's what we need to basically calculate. And so to calculate that, so we know that proper time is what? Is your dilated, so it's your dilated time over your Lorentz factor. So we need to first calculate your time dilated, which is quite easy. We've got all this information here. So we've got the distance basically, and we need to calculate time. We also got the velocity. Remember, this velocity is basically constant throughout these observers, because Einstein's secondary postulate says that the speed of light is the same for all observers basically. As you can see, yeah, so it doesn't matter. So this speed of light is the same for the astronaut, the same for the the Earth's observers. So yeah, so basically we can easily calculate the time dilated. So we can say that time that's dilated is basically your distance, which is your L naught basically in this case, over your velocity, which is basically 10.5 times. So how many light years each? So it says 9.46 times 10 to the power of 15, all being divided by your velocity, which is basically 0.85 times c, which is 3.0 times 10 to the power of 8. So 10.5 times 9.46 times 10 to the power of 15, all divided by 0.85 times 3.0 times 10 to the power of 8. So I get basically your time that's dilated is basically 3.89 to approximately 3.89. So 1, 2, 3, 4, 5, 6, 7, 8. 8 seconds. And now I'm going to put it into this formula to get the proper time. So my proper time is that 3.89 times 10 to the power of 8, all be divided by 1.90. I want to double check it. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. So that's going to give me 1.90. That basically gives me my time to be 2.05 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 seconds. So that's our proper time, and that's, we just need to get it in years. Basically, by dividing it by 60, we get it in minutes. Divided by another 60, we get it in hours. And we divide it by 24 to get it in a day. And how many? So 365 divided by another 365, we get in a year. So basically 6.5 years will take. It's a lot of time. Beautiful. Question 18. Alien astronauts are traveling between star systems aboard a cube-shaped spaceship as shown in figure 16. The sides of the cube along the x-axis, y-axis, and the z-axis measure to be this. So basically, yeah, they all have the same length in the spaceship's frame of reference. The spaceship passes Bob, who's on the spaceship, on a space station, at speed of this, all right? In the table below, determine the dimensions of the cube-shaped spaceship as measured from the Bob's frame of reference and explain your reasoning. Okay, this is a beautiful question. I've seen this kind of in the NEEP exam, so this is nice. So basically, what do we know? We know that length contraction only occurs in the direction of motion. So as this is going to the right, basically, as you can see from the velocity, it's going to the right. In the z, basically in the x-axis, this is where length contraction is basically going to happen. Only in the x-axis. Nothing's going to be affected in the y and z, basically. So what will be the measured? So basically, y and z are going to be the same, which is just basically 3.20 times 10 to the power 3. Also, this is 3.2 times 10 to the power 3. Yep. And of course, the side that's in x, which is parallel to the direction of motion, is going to be contracted, that length. It's easier to find the length contracted. So contracted length is L naught over your gamma, which basically is 3.20 times 10 to the power of 3 divided by 7.09. Writing this, so 0 times 10 to the power of 3, 7.09. Oops, why did I write that wrong? So 0.9. I basically get to how many? So to basically I get 4.51 times 10 to the power of, so 1, 2, to the power of 2 meters. So this here, these lengths that are in the x-axis, these lengths here, are basically going to be dilated, that are parallel to the x-axis. So this part here is going to be dilated. This also is going to be dilated. And this. So how would it look basically? It will look like this basically. So it will look like this. It will kind of shrink. So it basically looks like this. So the other ones are the same height. This is also in the same height. It's not the best. And this is also string, so you can see that's string. Basically, it will look like this cube here. So you can see that it's been strinked. Let me write that nice here. So you can basically, yeah, see how these value of the x, where it's in it, has been strinked, basically. And yeah, well, the other ones are still the same. That's it. Oh, yeah, your reasoning, yep, like what we said. So, length contraction. Occurs. So, oopsies. Occurs only in the direction of motion. So only x-axis gets affected and the others basically stay the same. So stay the same. Beautiful. Question 90. Is this the last question? Yes, it is. Let's smash through this question. In a nuclear fusion reaction in the sun's core, 2 deuterium nuclei, each with mass of this, fuse to produce 1 helium nucleus with a mass of this. Ignore the kinetic energy of the nucleus before the reaction. Calculate the energy released. Show working on. What a beautiful question to end the exam. So basically what happens is, in nuclear fusion, is especially in stars or the sun, is basically we have 2 particles. Basically, they're normally hydrogens, but in this case, what is it? It's deuterium. I think it's basically a hydrogen, but I think it has less mass, if I'm not mistaken. Yeah, so basically these are your 2 deuterium nuclei, and what they do is they fuse with each other. Basically, they're gonna come together and they're gonna be fusing, and they're gonna be fusing into a helium atom. So let's write that as that's a hydrogen. Now it becomes a helium atom, and so the total mass of these helium, of these hydrogens is basically double this, and it should be basically, and the mass of this here, your helium, was this over here. Now, basically, there would be basically some mass lost throughout this conversion, and that mass is going to basically be released as energy, basically. And that's what we want to do. We want to calculate the energy released. So what we're going to need to do is we want to calculate what's the mass that has been, lost. So what it is, it's basically, if you had first initially 2 of these, so 2 times 3.3436 times 10 to the power of negative 27 minus your final product, which is your 6.6465 times 10 to the power negative 20, and that should give you your energy change, basically, or the mass that has been lost, that has been basically converted to energy. 2 times 3.3436, so yep, 3436 times 10 to the negative 27 minus 6.64, so 6.6465 times 10 to the negative 27. So basically, I get a mass change is 4.07 times 10 to the negative 29. Easy. So now we've got that basically in kilograms. We're going to use rest energy, or your energy release, is mc squared. So basically that mass times your speed of light squared. Easy. And so that gives me basically a very big number. How many significant figures? Wow, it's just so much. All of them have 5. So I'm just going to write the whole thing. So 3 times 10 to the power of negative 12. And that is it. Beautiful. I hope you learned something through this video. Please make sure to like and subscribe for more future videos like this. And I hope, it helped a lot. And, goodbye, everyone. Take care of yourselves. Bye-bye.